Hey there, you know we use averages for pretty much everything, right? Average income, average score, average temperature. But here's the thing. The average can be a bit of a trickster. It often hides the most interesting part of the story. So today we're going to pull back the curtain and look at the story beyond the average and really dig into this idea of variation. All right, let's jump right in with a classic example. We've got two companies, Corporation A and Corporation B. They each hire 10 grads. Now, just take a quick look at the starting salaries. You can kind of feel the difference, can't you? Corporation A looks really consistent. All the numbers are bunched up together. But Corporation B, those salaries are all over the map. And here's where it gets wild. If you actually crunch the numbers and find the average salary for both companies, they're almost exactly the same, about $41,500. So if you only looked at that average, you'd probably think, hey, same offer, right? But we can see with our own eyes that's not the whole story, not even close. And that gets us to the real question, the one the average Joes can't answer. Which job offer is more predictable, more stable? Which one has more risk? To figure that out, we need a different kind of tool, one that measures the spread of the data, its variation. Okay, so let's start with the simplest, most obvious way to think about this spread. It's a concept you've probably heard of, maybe even used, called the range. This is our first baby step behind the curtain of the average. The range is, well, it's exactly what it sounds like. It's just the distance between the highest number and the lowest number. So for our nice, stable Corporation A, you take the max salary, 47 grand, subtract the minimum, 37 grand, and you get a range of $10,000. Super simple, right? Fast, easy. But, and this is a huge but, that simplicity is also its biggest flaw. Think about it. The range is built using only two data points, the absolute extremes. It completely ignores what the other 8 people are making. It tells us how big the playing field is, but it tells us absolutely nothing about where most of the players are standing. So to really get the full picture, we need something better. We need a tool that looks at every single data point. And that brings us to a much more powerful idea, measuring how each point deviates from the average. The idea of deviation is actually pretty straightforward. For each and every salary, we just ask a basic question. How far away is this number from our average of $41,500? A salary of $45K is a little bit above average, so it has a positive deviation. A salary of $38K is below, so it has a negative one. We're just looking at each point's personal distance from the center. So you might think, great, let's just average all of those deviations. Well, if you try that, you hit a brick wall. Because the average is the perfect balancing point of the data, all those positive deviations and all those negative deviations will always, and I mean always, cancel each other out perfectly. You add them up and you get 0 every single time. It's a total dead end. So how do we get around this zero-sum problem? Well, statisticians came up with this really elegant 4-step solution. First, you still find all the deviations, but then, and this is the genius move right here, you square every single one of them. Squaring a number always makes it positive, right? Problem solved. Third, you take the average of all those new squared numbers, which gives us something called variance. And finally, you just undo the squaring by taking the square root. And you can see that magic in action right here. For Corporation A, that deviation of negative 3.5 becomes a positive 12.25. The negative 4.5 becomes 20.25. Suddenly, all our numbers are positive, and when we add them up, we get a real, meaningful total. In this case, it's 88.5. We call that the sum of squares. So for the next step, we just find the average of that sum. We have 10 employees, so we divide 88.5 by 10, and we get a variance of 8.9. Now, this number is a measure of spread, but its units are kind of weird. In our example, it's 8.9 square thousands of dollars. What even is that? It's not super helpful for talking about salary. And that brings us to the last beautiful step. We just take the square root of the variance. The square root of 8.9 is right around 3. And just like that, by taking the square root, we are back to our original units, thousands of dollars. So the standard deviation for Corporation A is about $3,000. That number represents a typical distance a salary is from the average. Okay, a quick but really important side note here. So far, we've been treating our 10 salaries like they are the entire population. But what if they were just a small sample of, say, thousands of employees? Well, the symbols we use change a little, and so does one key part of the calculation. To get the sample variance, you divide by your number of entries minus 1. It's a small statistical tweak that actually gives you a better, more accurate estimate of the real variation in the whole population. All right, so we did all that math. We got this number, $3,000, but what does it actually tell us? What does a small standard deviation, or a big one, really, look like? Well, a small standard deviation looks like this. See how all the data points are just kind of huddled together? They're cozy, they're close to the average. This is our corporation A. The outcomes are really consistent and predictable. No big surprises here. But a high standard deviation, that's a totally different story. The data is just spread all over the place. This is Corporation B. There's way more variety, way more unpredictability. You might make a ton more than the average, or you might make a lot less. The standard deviation puts a number on that risk and that opportunity. And this is where it gets really cool. Because when your data has a certain common shape, the standard deviation basically gives you a statistical superpower. It turns out a lot of stuff in the real world, things like heights, weights, even test scores, tends to follow this classic, symmetric, bell-shaped curve. And for any data that looks like this, we can use a fantastic rule of thumb called the empirical rule. You might also hear it called the 68-95-99.7 rule. So here's how it works. Part 1. For any of these bell curves, about 68% of all your data will fall within one standard deviation of the average. So you take one step to the left of the average and one step to the right, and boom, you've just captured the vast majority of the typical values. Now, what if we take 2 of those standard deviation steps out from the middle? Well, now you're capturing a whopping 95% of all the data. In fact, statisticians often use this 2-deviation range as the benchmark for what's considered normal. Anything outside of that is getting pretty unusual. And if you go out 3 steps, well, at that point, you've got pretty much everyone, 99.7% of the data. Anything that falls outside of this 3 sigma range is a serious outlier. We're talking super, super rare. Okay, let's make this real. The average height for young women in the US is about 64.2 inches, and the standard deviation is 2.9 inches. So, using our 95% rule, we can do some quick math. 2 steps below the mean is 58.4 inches, and 2 steps above is 70 inches. And just like that, the rule tells us that about 95% of all young American women are between 5'10" and 4'10". Pretty powerful, huh? So, we started with 2 confusing lists of salaries, and we ended with a single powerful number. The standard deviation uncovers that hidden story of consistency, risk, and predictability that the average just can't tell us. It's used everywhere, from quality control in factories to risk management in the stock market. So the real question for you is, now that you know how to look for it, where will you see it next?